So what we're going to be talking about today is the concept of transient analysis. Okay. So what transient analysis literally means is that we are going to be analyzing a circuit when it is in a state of transition. So consider the following circuit where we have a short circuit, some current source IS like so, and then we're going to have a switch. And initially, our switch is going to be closed over here to the right at position B. And then at a particular instant in time, which we're going to call t is equal to 0, the switch is going to transition from being closed at position B to being closed at position A. Connected to position B of the switch is a resistor R and an inductor L. Everything here at the bottom shares this node. So for t is less than 0 minus, which we'll say is all time before switch changes state, our circuit is at what I'm going to call a DC steady state condition. All this really means is that we treat the circuit as if it were a DC circuit before our switch changes states. So for the circuit that I've drawn above, what that would look like would be something like this. Okay. So here's position A. It is open circuited. Here's B, and our current source is directly connected. Then we have our resistor R. And over here to the right, we are going to replace our inductor with a short circuit, because to a DC circuit, an inductor behaves like a short circuit. What I'm interested in understanding is what my inductor current looks like. So I'm going to call my inductor current direction down, and I'm going to call this current IL at 0 minus. Who among you can tell me what value IL of 0 minus should have? Same as IS. Absolutely correct. Thank you, Catherine. So all of the current from our current source is going to flow through the inductor none of it will branch off and flow through our resistor R, okay? Now, since there is current flowing through the inductor prior to the switch changing states, that means that there is energy stored in the inductor. Since we know that for an inductor, W is given by 1/2 L times the inductor current squared, right? So since the inductor current is non-zero, we have some amount of stored energy. Now let's look at what happens for all time greater than or equal to 0 plus. So this is all time after the switch changes state. Our circuit will look like this. So now our switch is closed at position A, and our current source is directly connected to the short circuit on the left. Here is going to be our open circuited terminal B. Here's our resistor R. And our circuit is no longer at DC steady state because there has been a change, right? So we can't be at a steady state condition if something has changed, especially if we're looking at it immediately after the change has occurred. So we can no longer replace our inductor with a short circuit, so we're going to have to leave it as an inductor. Like so, where this inductor is carrying a current IL of T. Okay. So what's going to happen for T greater than or equal to 0 plus is any energy that was stored in the inductor will be distributed to the resistor over time, okay, where that resistor will convert. Just a moment, Sarah, and I'd be happy to, okay? So the resistor is going to convert all of the energy that is stored by the inductor into heat, okay? So Sarah asked if I could explain again why the inductor can't be viewed as a short circuit after the switch is thrown. So immediately after the switch is thrown, the circuit is in a state of transition. Okay. And since the circuit is in a state of transition, because that switch effectively interrupted the behavior, the DC steady state behavior, we can no longer replace the inductor with its DC steady state equivalent. The instant that switch changes states, we go from a DC steady state condition into a transient condition. This might be a little easier to look at if I give you a plot of the inductor current as a function of time, okay? So actually, let me put my vertical axis here. Okay. So this is IL as a function of time. And then on this axis is going to be time. So based on the analysis that we've done a few moments ago, and let's call this value in particular, is, we know that for all points in time before t is equal to 0, our inductor current is a constant value, okay? So for this region of time, we have DC steady state conditions. Now, eventually, all of the energy that was stored in the inductor will be converted to heat by the resistor. If the energy that is stored by the inductor is 0, a long, long time after the switch opens up, that means that the inductor current has to be 0 a long time after the switch changes state as well. So let's call this time right here infinity. What it really means is just a long time after the switch has changed states such that the transient condition has died out. Everything to the right of this point in time is also a DC steady state condition. What we're talking about today is what's going on in this interval, which we're calling the transient state of the circuit. Okay. So what we are going to have to do to figure out what's going on is apply our circuit analysis techniques that we've developed up to this point, and we're going to have to introduce a little bit of calculus to figure out what's going on. Okay, so we're trying to figure out how the inductor current is behaving. What I'm going to do is I'm going to introduce a couple of voltage drops here. So let's call this VL of t, and I'm going to call this voltage drop VR of t. And I have chosen the positive polarity terminals for both of those voltage such that our inductor current IL of t is flowing into the positive polarity terminal of those components for t greater than or equal to 0 plus. So what I'm going to do now is I'm going to write a Kirchhoff's voltage law equation. It's going to be a pretty simple one. I'm going to start at the bottom left-hand corner here, and I'm just going to follow my current IL of t around that right-hand loop. And what I'll find is that VR of t plus VL of t has to equal 0. I can express both the resistor voltage and the inductor voltage in terms of my inductor current, right? So using Ohm's law, the resistor voltage is simply R times IL of t. And using the relationships that we developed over the last couple of class meetings, I know that the voltage drop over an inductor is given by L di by dt. This equation is an example of what's called a first order homogeneous differential equation. For those of you who have had Math 245, you already know how to solve one of these. For those of you that haven't, we are going to qualitatively figure things out here, okay? So effectively, what we're trying to do is determine what form must IL of t have to make our equation work? So effectively, IL of t has to be a function in which the function and its derivative could be added together to make 0. Another way to put that is that IL of t and the derivative of IL of t need to be effectively the same function other than some coefficients. So what function do we know of where it's the function itself and its derivative are effectively the same thing? E to the x, absolutely right. So we're going to assume that IL of t will be of the form A, which is just a scaling factor, E to the st, okay, where S is what's called the eigenvalue of the system, and it effectively tells us how quickly our exponential will decay. So if we plug in that guess value into our differential equation, what we'll have is R times A e to the st plus L times S A E to the st, because when I take the derivative of A e to the st, I get back S A e to the st. I'm going to set this equal to 0. And now what I'm going to do is simply factor out terms, right? So there's a common factor of A. And let's call this R plus L times S. There's a common factor of E to the st as well. And our goal now is to figure out, well, what makes this thing go to 0? Well, if A is 0, this equation goes to 0. That is a trivial solution. And effectively what it represents is the case where the inductor didn't have any energy stored in it to begin with. Okay. But we know that's not true. E to the st will trend towards 0 if S happens to be a negative quantity. But we have this bit right here in the middle. I'm just going to underline it. This is the characteristic polynomial of our system. And it tells us what specific value of S based on our circuit parameters forces our equation to be 0. By inspection, we can see that S needs to be negative R over L. When S is exactly equal to negative R over L, our characteristic equation that I've underlined in orange is 0, and therefore our whole equation is equal to 0. So we figured out what S has to be. So we know this bit right here. Well, now we need to figure out what A is. let me go to the next page here and summarize some things. All right, so we have assumed that our inductor current IL of t is of the form A e to the st. We have figured out that S in this case is negative R over L, which means IL of t must be something A e to the negative R over L times t. Our goal now is to figure out what A is. So how we're going to do that is we're going to look at IL of t at 0. So let me scroll back up here. I believe it was Catherine. Let me double check so I'm not misattributing things. Yes, it was Catherine who determined that the inductor current at t is equal to 0 minus was IS, the current that's being supplied by the current source. Well, we know, or at least we learned the other day, that the current flowing through an inductor cannot change abruptly, which means that the current flowing through the inductor at t is equal to 0 plus, the instant the switch changed positions must also be IS. So from that, if we evaluate IL at 0 plus, would have to be A e to the negative R over L times 0. Well, e to the 0th power is just 1. So A has to be whatever the inductor current was the moment after the switch changed states. From that, we find that our inductor current is going to be IL at 0 plus, which we're going to consider our initial condition on the system, multiplied by a factor of e to the negative R over L times time. I'm going to put a box around this because it's a very important revelation. And then we're going to go back to our graph and effectively fill this in. So what we should observe for this circuit, and really any circuit which contains resistors and inductors, is that our current will exponentially decay from some initial value down to 0. And the current during the transient condition is simply the initial condition, IS, multiplied by e to the negative R over L times time. So the rate at which our current decays is dependent on the resistor value and the inductor value in our circuit. Now, we know what the shape of the inductor current is, right? It's this exponential, what I'm going to call response. So let's think about what the shape of the voltages would have to be if the current IL has this exponential response, right? I'm going to do this kind of as a quick aside right here. So our resistor voltage, VR of T, by Ohm's law, has to be R times IL of T, which is then going to be R times IL of 0 plus E to the negative R over L times time. Or VR at 0 plus E to the negative R over L times time. Since the voltage drop across the resistor at T is equal to 0 plus has to be R times whatever the inductor current was. Similarly, we can say that VL of T has to just be negative VR of T, which we could write as VL of 0 plus E to the minus R over LT, where we know that VL of 0 plus is just negative VR of 0 plus from Kirchhoff's voltage law. So what I'm trying to get at here is that our inductor current has an exponential response, and it forces the voltages to also be of that same exponential shape. So in general, we can say that for an RL circuit, which is any circuit that contains resistors and inductors, Y of T, where Y here represents any voltage or current in our system, must be of the form Y at 0 minus for T less than 0 minus, and it must be of the form Y at 0 plus E to the negative R over L times time. Let me make sure that L looks like an L. For T greater than or equal to 0 plus. This generic equation works for any resistor voltage, resistor current, inductor voltage, or inductor current in an RL circuit. Okay. So I'm scrolling down through my previous notes, and what I'm going to do here is we are going to work a simple example that proves that to be true. So let's start off with something fairly straightforward. Okay. Let's say that we have the following circuit. where we have a 3 amp source connected in parallel to a 5 ohm resistor. And then we're going to have a switch. And this switch will open at t is equal to 0. On the right-hand side of the switch, we are going to have a 10 ohm resistor and we're going to have a 1 Henry inductor. The quantities of interest that I want us to determine are going to be the inductor current IL of t, the inductor voltage VL of t with this particular polarity, and the resistor voltage VR of t with this particular polarity. Okay, and we're going to talk our way through the steps that we will use to analyze a circuit like this based on what previous knowledge that we've gained. So step number 1 will be to analyze the circuit at t is equal to 0 minus. Recall that this is a DC steady state condition, and therefore we're going to need to replace our inductor with its DC steady state equivalent, which is a short circuit. Okay, so at t is equal to 0 minus, our circuit looks like this. Our 3 amp source is happy being a 3 amp source. Our 5 ohm resistor is just a 5 ohm resistor. Our switch is closed at t is equal to 0 minus, so I'm going to replace my switch with a short circuit. Then I have my 10 ohm resistor here, and I'm replacing my inductor with a short circuit because we're at DC steady state. I'm going to identify our quantities of interest. So here is IL at 0 minus. Here is VL at 0 minus. Here is VR at 0 minus. I would like some help from you guys, if at all possible, in determining what these quantities are. Does anybody have any thoughts about any of those 3 values? So Devarier has suggested that IL of 0 minus is equal to 3 amps, and he is absolutely correct. Anybody have any thoughts on either of the 2 voltages? So the inductor is being replaced by a short circuit at t is equal to 0 minus. What does the voltage drop over a short circuit have to be? Zero. Absolutely right. Thank you, Devarier. So VL of 0 minus has to be 0 volts because it's the voltage drop over a short circuit. Since our 10 ohm resistor is in parallel with that short circuit, what does the voltage drop over the 10 ohm resistor have to be? Also 0. Thank you, Catherine. So we have determined the values of all three quantities at t is equal to 0 minus. Does anybody have any questions, comments, or concerns about the analysis that we did to get these three values? All right, let's move along to 2. Sorry. So step number 2 will be to analyze the circuit at t is equal to 0 plus. Now, earlier when we were figuring out how things worked, we looked at the circuit for all time greater than and equal to t is equal to 0 plus. Step 2 here is just effectively taking a snapshot. We want to know exactly how it works at t is equal to 0 plus. We don't care about any other point in time, okay? So this is the beginning of the transient condition. So at t is equal to 0 plus, our switch has just opened. So we're going to have our 3 amp source here, our 5 ohm resistor here. Our switch is going to be replaced by an open circuit. And then here's our 10 ohm resistor. And over here to the right is going to be my inductor. I'm not going to draw an inductor, okay? And so I feel like I'm going to need to explain myself. We know that the current flowing through the inductor cannot change from t is equal to 0 minus to t is equal to 0 plus. So whatever current the inductor was carrying at t is equal to 0 minus, the inductor has to be carrying that exact same amount of current at t is equal to 0 plus. In this case, it's 3 amps, okay? So what I'm going to do is I'm going to replace my inductor at this very specific instant in time with a current source, which has the same direction as IL at 0 minus and the same magnitude as IL at 0 minus, because we know that the current has to be the same direction and magnitude of IL at t is equal to 0 plus. So I'm drawing this as a 3 amp current source. And this is specifically because IL at 0 plus must equal IL at 0 minus. So now I'm going to identify my quantities. Sorry, that should be a VR, not a VL. IL at 0 plus has to be 3 amps. So what should VR at 0 plus be? $30 volts. Thank you, Catherine. I'm going to assume that you got that result using Ohm's law. Simply 10 ohms times 3 amps is equal to 30 volts. Actually, I'm going to write that down just in case people don't see it intuitively. 10 ohms times IL at 0 plus equals positive 30 volts. And the last thing that we need to determine is VL at 0 plus. Let me draw that better. VL at 0 plus should be negative VR at 0 plus, because these two elements are in parallel, but the voltages are defined with opposite polarities. And from this, VL at 0 plus must be negative 30 volts. Does anybody have any problem with the analysis that was carried out at T is equal to 0 plus? All right. So step 3 here, and when we get a little bit more experience with these type of circuits, we're going to call this something slightly different. But for now, step 3 is going to be determine REQ and LEQ during the transient condition. So during the transient condition means for all time greater than 0 plus. Since we're determining equivalent resistances and equivalent inductances, I'm going to use a dead network representation, and it's important for us to do that, okay? Effectively, we're finding the Thevenin equivalent resistance as seen by the inductor, and then we're going to find the Thevenin equivalent inductance as seen by that resistance, okay? So the dead network representation of my circuit is going to have a short circuit. Oh, excuse me, that's not correct. It's a current source, so it should be an open circuit. My apologies. Here is our 5 ohm resistor. During the transient condition, our switch is opened. Here is our 10 ohm resistor. Here is our inductor, which I said was a 1 Henry inductor, right? Let me scroll up to double check that. All right, so if we want to find the equivalent resistance with respect to the inductor, what do we need to do? So I'm just going to write here, dead network during transient condition. Now, find REQ, or R Thevenin, I guess would be a better way to put this. Find R Thevenin as seen by the inductor, okay? So to find the Thevenin equivalent with respect to a particular component, which is what we're doing here, we have to take the component out and look in through the terminals left over, right? So we're looking in through here and trying to find RTH. What is it going to be? $10 ohms, exactly right, Devarier. The 5 ohm resistor isn't going to contribute anything. Another way to think about this is effectively, what's the only resistance, or what combination of resistances are left connected to the inductor? So in this case, either way that we look at it, it's just the 10 ohm resistor. Well, since we only have a single inductance, it's fairly obvious. Let's write this as REQ. That LEQ has to be 1 Henry. You will be given problems that have multiple inductors, and you will be expected to employ inductor combination techniques to determine what the equivalent inductance of that network is. But for this particular problem, we're not going to have to face that. So we know REQ and we know LEQ. So now we can move along to step 4. Step number 4 is simply plug results in to our generic equation. So since it's been a moment since I've had the generic equation on screen, I'm going to write it down again. Our generic equation, y of t, is equal to y at 0 minus, the t less than 0 minus, the y at 0 plus, e to the negative r over L times t, for t greater than or equal to 0 plus. Can I explain how the 5 doesn't contribute? Absolutely. Let me scroll back up here. So let's identify our nodes. So we have this node on top. This node on bottom. And this node on the top left, right? So we are trying to find the equivalent resistance seen between the red and the blue nodes, or we could call it terminals A and B or whatever we wanted, right? So the resistance of 10 ohms is directly between the red node and the blue node. Let 5 ohm resistor is between the green node and the blue node. And because the green node isn't in any way connected to the red node, the 5 ohm resistor can't be contributing to the equivalent resistance, right? So just to make sure this is super clear, if we had a network that looks something like this, let's call this an 8 ohm resistor, we would actually have to do some sort of resistor combination techniques, because this would look like 13 in parallel with 10 when we're looking in through that right-hand set of terminals. But because we have that open circuit from the switch, disconnecting the 5 ohm resistor from the inductor, the 5 ohm resistor doesn't show up in our equivalent resistance. Okay. All right, so all we're going to do here is we are going to plug stuff in to our generic equation, right? So at t was equal to 0 minus, our inductor current was 3 amps. For t is equal to 0 plus, our inductor current was 3 amps. And then we're going to have e to the minus, R was 10 ohms, or REQ was 10 ohms, and L was 1 Henry. So this is going to look like 10 over 1, or negative 10 t amps, for t greater than or equal to 0 plus. For our inductor voltage, at t is equal to 0 minus, our voltage was 0 volts. At t is equal to 0 plus, our voltage was negative 30 volts. E to the negative 10 t volts, for t greater than or equal to 0 plus. And lastly, we're going to have the R of t, which was 0 volts for t less than 0 minus, positive 30 volts at t is equal to 0 plus, and then e to the negative R over L, which comes out to be 10 t volts for t greater than or equal to 0 plus. Now, we have a way to check our results here, okay? So what I mean by that specifically, let's do this in blue, is that we know the voltage drop across an inductor is supposed to be equal to L times the derivative of the inductor current. Right? L in this case was 1 Henry, where a Henry is a volt second per ampere. And now we're going to have the derivative with respect to time of e to the negative 10t. Sorry, 3 e to the negative 10t. I had a total brain fart there, amps. So how do I take the derivative of 3 e to the negative 10t? Well, I can take the 3 amps out. So we're going to have 1 volt second per amp times 3 amps. And now I'm just taking the derivative of e to the negative 10t. When I take the derivative of e to the alpha x, let me write this up here just so it's very clear what I'm doing. I believe I introduced this the other day, but the derivative of e to the alpha x is alpha e to the alpha x. Well, in this case, alpha is just a factor of negative 10. With some blue. Since this eigenvalue is acting on it, so actually it represents R over L, right? So just let's do this over here to get the units. So resistance R over L is going to look like volts per amp divided by amp seconds, excuse me, volt seconds per amp. I got it backwards. So that's volts per amp multiplied by amp per volt seconds. Volt cancels volt, amp cancels amps, and we're left with units of per second. E to the negative 10t. So this amp is going to cancel this amp. This second is going to cancel this per second. And so I have 1 times 3, which is 3 times negative 10, negative 30, e to the minus 10t. So doing the long calculus way gives us the exact same results as just plugging stuff into our generic equation. So I would argue that plugging stuff into our generic equation is the easier route, and it makes the analysis pretty straightforward. Okay. So this is our general procedure. Let's work another problem where we're going to increase the difficulty by really quite a bit, but we're just going to apply the exact same few steps here. Okay. So this is going to be our circuit of interest. Where this is a 180 ohm resistor. Here we have a 90 ohm resistor. This is going to be an 18 volt source that is connected to a switch. And our switch opens at t is equal to 0. Here we have a 1 millihenry inductor. Here's a 50 ohm resistor. Here's a 3 millihenry inductor. Here's a 2 millihenry inductor. Let me close this off. At the bottom. Our ultimate goal here is going to be to determine this current, which I'm going to call Ix of t as a function of time. Okay. Now, because how the inductor current behaves at t is equal to 0 minus influences how things are going to appear at t is equal to 0 plus, we're also going to have to pay attention to our inductor current, which begs the question, which inductor current should we be looking at? Should it be just one of them? Should it be all three of them, etc.? Okay. So I told you guys that this problem is a significant increase in difficulty. So the first thing that we could do to, even before we start analyzing this circuit, would be to simplify. Okay. So I'm going to copy this circuit, and then I'm going to ask you guys a question. If I swap the placement of the 50 ohm resistor and 1 millihenry inductor, is that going to change the behavior of the circuit at all? No. Whenever two elements are connected in series, like that inductor and resistor are, I can change their order and it doesn't harm anything. Okay. The reason that I change the order of those two elements is because now I can see that I have a 1 millihenry inductor connected to a 2 millihenry inductor that's in parallel with a 3 millihenry inductor. Okay. Effectively, I could slap a set of terminals right here and replace everything to the right of those terminals with a single equivalent inductance. So let's go ahead and do that, right? So what is the equivalent inductance that we see to the right of those terminals that I've drawn in red? So since inductors in parallel combine like resistors in parallel, 2 millihenries in parallel with 3 millihenries is going to look like 6/5 millihenries. Then I add 5/5 and I get 11/5, which is the exact same thing Devarier said. And 2.2 is also 11/5. So Sarah was also correct. Okay. So let's replace this whole thing here with a 11/5 millihenry inductance. Okay. Now, I'm going to consider this current to be IL of t, where I no longer need to worry about how it splits among the inductors or anything like that. I've just lumped all of my inductors together. And I can do that because my goal here wasn't to determine the inductor current, it was to determine that resistor current, which is influenced by how the inductors are behaving. Okay. All right, so now that we've got some simplifications taken care of, we're actually in a place that we can start analyzing the circuit. Okay. So we'll start with step number 1, which is to analyze the circuit at t is equal to 0 minus. At t is equal to 0 minus, our switch is closed. And so I'm going to redraw this a little bit differently. So here's my 180 ohm resistor. Here's my 18 volt source. Here's my 90 ohm resistor. Here's my 50 ohm resistor. And then the short circuit here to the right represents my inductor. So let me just make sure that I've done this correctly. So effectively, that thing I've circled in orange is supposed to be this node. And this thing that I've circled here in pink is supposed to be this node. I believe I have redrawn this circuit correctly, right? All right. So erase this big ugly blob. Now I'm going to identify my quantities of interest. Oops. Sorry, this should be 0 minus, and this guy should be 0 minus as well. So who has thoughts on how I can determine either of those quantities? I'll just put Ix of 0 minus over here, and IL of 0 minus here. Anybody have any ideas? Oh, Sarah, you're making this far too complicated. What's the voltage drop over the 90 ohm resistor? You got it right there, Devarier. So effectively, we can just use Ohm's law. The voltage drop across the 90 ohm resistor is 18 volts. And so 18 over 90 is going to look like 2/9 of an amp. How do we find our inductor current? Well, the inductor current is the same as the current that's flowing through the 50 ohm resistor. So that should just be 18 volts over 50 ohms, which is going to look like 9 over 25 amps. So there isn't anything wrong with Sarah's suggestion of applying mesh analysis. It absolutely would have gotten us the results. However, because all of these elements are connected in parallel to a voltage source, actually setting up that system of equations is a bit of overkill for this particular situation. Just as a heads up, some of you are well aware of this about me, but I am a jerk that likes to give you situations like this where mesh analysis or something like that would be very easy to apply. But if you just look at the circuit for a minute, you might find an easier way to approach it. So how I typically work is I start by looking for Ohm's law relationships, then I go KCL and KVL, voltage division, current division. I don't get to nodal and mesh analysis until the end of how I'm trying to decide how to analyze a circuit. I look for a less complicated method first. And the reason why I look for those more fundamental methods first is because I know that I make mistakes when I set up systems of equations pretty regularly, which I'm sure you guys have noticed at this point as well. So I try to come up with a way to solve for things without having to set up a system, if at all possible. All right, so anybody, no problem at all, Sarah. I'm sure lots of other people were thinking mesh as well. And like I said, there's nothing remotely wrong with it. I just want you guys to start looking for some of the easier relationships. All right, so how do we feel about the analysis that we did at t is equal to 0 minus? Anybody have any questions, problems, or anything like that? All right, so let's look at the circuit 0 plus now. So at t is equal to 0 plus, our switch has opened. And so that's going to disconnect the 18-volt source. So how I'm going to draw this is like this. So here's my 180 ohm resistor. Here's my 18-volt source. Since my switch is open, the 18 volts is disconnected. Here's my 90 ohm resistor. Here's my 50 ohm resistor. And I drew that one too long. Much like I did in the previous example, I'm going to replace my inductor with a current source having the same direction as IL at 0 minus and the same value as IL at 0 minus, which I believe was 2/9 of an amp. And we now need to figure out what Ix of 0 plus is. And just for the sake of argument, IL at 0 plus. But we know that IL at 0 plus must equal IL at 0 minus. So that's going to come out to be 2/9 of an amp for sure. If the value of IL at 0 plus changes from what it was at 0 minus, you have made a fundamental mistake. I cannot emphasize that enough. I'm sure several of you are accidentally going to do it. So I'm just trying to harass you into believing me not to change the value of IL from 0 plus to 0 minus, or from 0 minus to 0 plus, excuse me. All right, so now we need to talk about how we get Ix at 0 minus. Thank you. You're very correct, Justin. I put the wrong thing down. IL was 9/25. Ix was 2/9. I transcribed the wrong thing. So thank you very much for pointing that out. All right. So shouldn't harass you guys about making mistakes when I make the exact same one I'm trying to convince you not to make. So that's karma biting me in the butt. Oh well. All right, how do we solve for ix at 0 minus? So Devarier, that would be true if current weren't able to flow through the 180 ohm resistor on the left-hand side of the circuit. Right? So our inductor current IL is going to flow down, and it's going to hit this node. Some of it can flow up this way. Some of it can flow up that way. So it's not going to be as simple as negative IL in this particular case. Anyone else have a suggestion? Current division. That's how I would approach it as well. We could also do mesh here, but I think current division is a very reasonable thing. All right, so let's write this down here. Ix at 0 plus is going to be our inductor current. Oh, and I forgot to change it here. So this should be 9/25. And then we have the branch we want, which is going to look like 1 over 90 ohms. And then we're going to have 1 over 90 ohms plus 1 over 180 ohms. Recall also, though, that, and I literally just had this drawn, I guess I shouldn't have erased it yet. The expectation here is that this current's going to hit this node, and some of it's going to split and flow up like that. The rest of it is going to split and flow up like this. The direction of Ix is opposite the direction that we expect the current to flow when it splits. So we need to make sure to include that negative sign. And let's throw this into a calculator. Which means I have to find my calculator. Give me just a moment. I got negative 6 over 25 amps. If anybody else happened to put that into the calculator, could you please let me know whether or not you got the same result? Awesome. All right, sorry, and this should be 0 plus. Okay. So now we're ready, unless anybody has any questions or comments. I believe we're now ready for step number 3. Determine LEQ and REQ during the transient. So looks like I'm going to have to do this on the next page. So during the transient condition with a dead network, we are going to have the 180 ohm resistor. Our 18 volt source is going to be a short circuit. Here we have our 90 ohm resistor. Here we have our 50 ohm resistor. And here we have our 11/5 millihenry inductor. So right from the jump, we know that our equivalent inductance LEQ is 11/5 millihenries. We already figured that out much earlier on in the problem. Now to determine our resistance, we are going to simply remove our inductor. And look in and figure out what it is that we see. Anybody have any thoughts? So I believe, I do not agree with that, Devarier. Let's look at the nodes to see why. So here's one node. There's another node. And then here's this node. So the 180 ohm resistor and the 90 ohm resistor are in parallel because they are between the blue and the red nodes. The 50 ohm resistor isn't in parallel because it's between the orange and the blue nodes. So to me, this looks like 50 ohms in series with the parallel combination of 90 ohms and 180 ohms. Which, if my mental math is correct, is 110 ohms. All right, just checked it on my calculator to make sure. Does anybody have a problem with REQ being equal to 110 ohms? All right, so from here, we would simply move along to step number 4. Plug stuff in. So since we're interested in the behavior of IX, we will have IX as a function of time. So what was the value of IX at t is equal to 0 minus? I believe it was 2/9, but let's check. Yes. What was the value of IX at t is equal to 0 plus? I believe it was -6/25. That seems right. e to the negative. All right, so we have R is 110. And L is 11 over 5 times 10 to the minus 3. So 110 over 2.2 millihenries looks like negative 50,000 T amps for T greater than or equal to 0 plus. And I'm just going to put an arrow here just to make sure. This is 110 ohms divided by 2.2 millihenries. All right. I'm going to stop talking for today. On your homework assignment and even on your in-class assignment, actually, for this material, there are circuits that have capacitors in them. So what we're going to kick things off with when we get to class on Monday is the how to analyze an RC circuit. We're going to go through that derivation pretty quickly because it's going to be extraordinarily similar to what we did today for these RL or resistor inductor circuits. And then we're going to introduce the concept of the time constant, where we'll get a generic expression that's valid for any circuit containing energy storage elements. And then from there, we will move on to total response. So we're going to have a busy day on Monday, but I feel like I've talked enough for today, and so I'm going to leave you guys be. If you have any questions about what we've covered today, I'd be happy to answer them. If not, I hope you all have a great rest of your afternoon.